Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through Intro to Magnetic Circuits, which is a topic under Applied Electricity. In our previous lessons, we've gone through the three-phase system, gone through the AC as well as the DC circuit. So we move to the magnetic circuit. If this is the first time you have been on this channel, kindly subscribe to support and please stay tuned for any future tutorials. What do we mean by a magnetic circuit? So you generally know that a circuit is simply a closed loop, right? So if you have any closed loop, we say we have a circuit. But here the new term is what we call magnetic. In our DC, you realize that we have what we call a power source connected to a load and connected back. There is a flow of electrons, right? Which moves around our circuit and returns back. So that is a circuit. So the idea of a circuit is a closed path, a closed path. In the context of magnetic circuits, we have a closed path, but our interest is a magnetic flux. What represents current in our usual circuit? Let me give you a simple diagram for explanation. Now, we don't use wires here. We use a block of iron, right? So I have a block of iron here like this. So this is what you call air gap. I'll explain it very soon. Air gap. I have one part of it which is being wounded by a coil of wire. Okay. And this coil of wire is being supplied with current I here. Okay. Then there is N is the number of turns. Okay. The number of times this wire has been coiled is what you call N. Okay. This produces a force here called F. I'll explain each term. And this force here generates a magnetic effect in this particular section. In turn, this magnetic effect produces what you call a magnetic flux, which moves around the circuit to cause a closed circuit. Okay, so this structure that I have here is a simple magnetic circuit. Now let me explain the terms. The first term I'm going to explain is what we call magnetomotive force. Magnetomotive force. What do I mean by magnetomotive force? Magnetomotive force is simply a force which generates a magnetic flux within a circuit. So it's simply MMF and similar to EMF in our normal electrical circuit. Okay. So magnetomotive force is simply your voltage source, or let me say the potential difference. Okay. And we say that F is equal to Ni, which is the number of turns of wires times the current passing through, gives us enough force which generates magnetic flux. So here you can see the number of turns is simply a number. I is amperes. So the unit is what? Amperes turn, or simply amperes. That's all. So wherever we are doing anything and you see AT, it means that is your magnetomotive force, or you can see A is the same thing. It doesn't change. So this magnetomotive force represents our voltage source which generates our current now, which we call magnetic flux. So now let me label magnetic flux and we talk about that. We use this symbol magnetic flux. Now, once we have our source will generate what we call magnetic flux. Okay, so magnetic flux is represented with this symbol. Take note. Anywhere you see this, we are dealing with magnetic flux. So with this magnetic flux, what we are trying to say is the same as the current, you know. So the current in our circuit, which we say is flowing, once generated from the source, which is our magnetomotive force, this is generated across. Okay, so this is our iron bar. So this is iron here in what do you say, magnetic circuit. We don't use wires, but we use what? Iron bar. See where the wire is. The wire is simply being coiled to generate our force. That is all. But we use a block of iron as our conducting circuit. That's beautiful, right? So this is our iron. Now I've explained magnetic flux. So what do you think the unit of magnetic flux would be? We call it Weber. Weber, named after a scientist. So capital W, small b, Weber. So wherever I see Weber, that is a magnetic flux. Okay. Now, another thing you see here is air gap. One beautiful part of magnetism is it can jump spaces. So the air gap here still doesn't affect the breakage or doesn't break our circuit, as you know in open circuit. Okay, electron doesn't have the ability to jump, but magnetism here, it simply induces its magnetism at this side and the flow continues, and simple as that. So these are some few terms that we're going to highlight. Now let's enter another part which we call flux density. Flux density. When you talk about flux density, we are trying to say, okay, it's represented as B, okay, capital B, and the formula is given as our magnetic flux over area. So in magnetism, for us to know how strong how strong a magnetic effect is felt at a particular point, it dependent on two things: the magnetic flux at that point and the area. So you can see that if you have a very small area with a very high magnetic flux, that place will be felt strongly. So the magnetic flux density is simply talking about how strong the magnetic effect is felt. So wherever you have a larger area, obviously your magnetic density will go down, right? So the unit of our magnetic flux density is given as what? Weber per what? Meter squared, as you can see from here. This is Weber and this is area per meter squared. As simple as you can use the word Tesla. So you've heard Tesla, Tesla, Tesla. So Tesla, which is named after Nikola Tesla, is the unit of flux density. Anywhere you see it, flux density. Okay, let's go ahead and talk about what we call magnetic field intensity. Magnetic field intensity. It is represented as H. So wherever you see H, we are talking about magnetic field intensity. This is flux density, where we are talking about the flux per area. This is field intensity, and it's simply defined as capital F over L, your magnetomotive force over the length of the section we are talking about. So the field intensity is simply dealing with sections of your magnetic circuit. So when I take a section of length L, what is the force which is being felt there? Please don't confuse yourself with the flux density. Okay, flux is just a simple lines. Remember that if I have a magnet here, you throw some lines here, right? So the lines that this magnet will throw is what we call the flux, right? Lines. But magnetomotive force here is like you calculating the voltage across a particular point. I don't know if you get it. So if I have my circuit here and I want to find the voltage across this what do you say, load, which is the resistor, you know that it will be a part of my total voltage. So apply the same thing here, where I have my F being the total voltage, the voltage across that particular point over the length, right? That is what gives us magnetic field intensity. The unit is very simple. The unit is you know, this is ampere turns or ampere, right? So the unit becomes ampere 80 per hertz meter. As simple as that. Now let's go to one beautiful thing here too. But since we have done B, we have done H, we have what we call the BH curves, B to H curves. So this gives us the relationship between magnetic flux density, B, and the magnetic field intensity, H. What is the relationship between these two? For us to understand this relationship, we have what we call um, magnetic permeability. So magnetic permeability, okay, which is represented as mu. So mu here, we can have mu naught or mu r. Okay. So mu naught is magnetic permeability of free space, and mu r is of a medium. So depending on the medium, you have the magnetic permeability. The idea is that if we are saying that a magnetic effect is being generated by our force, magnetomotive force, every material would allow a level of permeability of this magnet so that the quantity of magnetic flux that will be flowing may also have influence, or may be influenced by the material property. Using an iron and using a steel, or using bronze or something, right? They will all have different inherent properties that will affect the flow of flux. Therefore, the permeability is the idea that the amount or of the inherent ability of a material to allow magnetic flux to flow through it. That is all. So B to H curve. So the formula relating B. So anytime you see B, you can relate it to H as mu naught H. This is when you are dealing with free space. So a typical example is an air gap. Yeah. So this air gap here, you realize that the magnetic flux will just pass through, right? At this point, if I want to find my magnetic um, flux or my magnetic field intensity, the formula becomes B is equal to what? Mu naught H, because it's permeability of free space or air. The only resistance or the only parts considered here is air, because there's nothing here. But when I come to this material, it is a different thing. This is where I get B to be equal to mu naught times mu r times H, because it will be the magnetic permeability of free space times the magnetic permeability and relative permeability of the material. That is what you should take note of. So these two formulas is very important in the course. Okay. Then now let's talk about one beautiful thing. We call it reluctance. Reluctance. You realize that in electrical circuits, we have what you call resistance. Is that not it? Resistance. So resistance is the opposition of current in any circuit. Similarly, there should be opposition of magnetic flux. So that's what we call it, reluctance. Okay, reluctance. So reluctance is simply the opposition of magnetic flux across any section in the magnetic circuit. So by next time, I know you know F should be equal to our magnetic flux times what? Our reluctance. Reluctance like this. This is one beautiful formula like an Ohm's law. So our voltage is equal to our current times what? Our resistance. Here our resistance is reluctance, our current is our magnetic flux, and this is our magnetic force. Take note of that. Now, generally, you know that a resistor is a resistance of resistor is what rho L over what E, right? Similarly, we have reluctance, which is going to be equal to generally reluctance equal to L over mu naught multiplying mu R times. This is the general formula for a reluctance. The length of the material or that section over its permeability of free space times its relative permeability times the area. That gives us our reluctance. So once you find this, you can come and put it in the formula to find your magnetic flux or vice versa. So here, my R is either equal to this or what? F over what? My magnetic flux. Take note. So these are relatable, and I believe that at this point you should be familiar with all that I have been saying. Now, the inverse of reluctance is what we call permeance. Permeance. So permeance is the opposite of reluctance, and permeance is also the same as the conductance in our DC and the AC circuit. So in an electrical circuit, you have what we call conductance, which is opposite of resistance. Here, the opposite of reluctance is permeance. Take note of that. The symbol of permeance is this, okay, and it's simply equal to 1 over what? Our reluctance. Simple as that. That will become what? Mu naught, mu r, okay, all over. Simple as that. Thank you for being with me in this video, and please don't forget to subscribe and share. See you in the next video as we solve a typical magnetic circuit problem.